start. We can start.
So it's a great pleasure to have Lenaic here giving us a talk. Lenaic is a professor at the math department here at EPFL, leading the DOLA group. Looking forward to your talk.
Thank you. So we'll press, yeah, play. Okay. So thank you for the introduction. So we are going to enter into a different world after the world of music. Here we're going to talk about barycenters. So this will be a slightly like mathematical talk, but if you have any question or if any notation is unclear, please do not hesitate to interrupt me. We can make this interactive. So I want to talk to you about an object which somehow I bumped into while I was doing researches on a slightly different topic. I will come to it in the third part of my talk. I was working on some optimization algorithms, and I realized that there is some notion of barycenter with very nice properties into one object, and so I want to tell you a bit about this object. So tractable barycenter for probability measures in machine learning. So by tractable, I mean that it's both theoretically tractable and also in practice. I want this to be an object that you can also use in applications. So what do I have in mind when I talk about barycenters in the space of measures? Well, this is, as you imagine, you have several probability measures. Here I have plotted 3 probability measures called nu1, nu2, nu3 on the two-dimensional plane. And I want to have a notion of barycenter or a notion of probability measure which averages the 3 of them. So I want to understand a notion of barycenter in the space of probability measures. And this can have many nice applications. One of those is, for instance, if you have a large task where you want to compute some posteriors of Bayesian computations, but it's a too big task, then you can separate it into smaller tasks. This is a nice paper by Chizat and co-authors. You can separate it in smaller tasks and then combine all your posteriors into a single object using the barycenter of these probability measures. So whenever you have several probability measures that you want to summarize in one object, you want to define a good notion of barycenter between probability measures. And you see that in this kind of applications, we are dealing with large-scale objects. So we have a large number of points which define our probability measures. Usually, they are only defined via samples. We do not really have access to densities, but only to samples. We are in high dimension. So we want some object which behaves well in all these, in this context, which is a large scale. We might also have a large number of probability measures. Here, I just plotted 3, but we might have a large number of them. Okay, so that's the object. And the approach that we will take, which is somehow very natural, is related to optimal transport. So before I define what is an optimal transport barycenter, which is in some sense the most natural notion of barycenter between probability measures, I need to introduce some technical definitions. So I will always consider in this talk X to be a compact convex subset of RD. So D is the dimension of my space and X the subset, dx the Lebesgue measure, and let's take mu and nu, 2 probability measures on this set. So the notations I will use here, this is for the relative entropy. This is also known as the Kullback-Leibler divergence between mu and nu. This is noted H nu nu, okay? This standard definition. And the Kullback-Leibler divergence between mu and the Lebesgue measure. This is a negative differential entropy. It will be denoted H of mu. So all these functions are convex. And now that I've defined this, I can define entropic optimal transport. So this is a certain regularization of optimal transport. Let me go through the definition step by step. So first, we choose a notion of cost, C, which tells us when I take 2 points in my space, what is the effort that is required to move from one point to the other. So usually you can think of this as the distance between 2 points or the square distance between 2 points. And then you consider the set of transport plans, mu nu, which I will define in the next slide. And over all these sets, you want to minimize some convex optimization problems. So what is a set of transport plan? This is the set of ways to move the mass from a probability distribution nu to another probability distribution nu. So here is the definition. This is formalized as a probability measure on the product space x times x, such that the first marginal is mu and the second marginal is nu, representation with one-dimensional distribution. Gamma here is a transport plan. here it tells us that if I take a point in mu, it will be scattered through all the distribution in mu. So here, this is the product coupling, which is one example of transport plan, which is the most simple transport plan. But you have also more special transport plans. For instance, gamma here, this is a transport plan, which is concentrated on the map, which tells us that the point of mass of nu here will be transported to this point of mass of nu here. So transport plans are probability measures on the product space, and they're used to describe a way to move the mass from nu to nu, or symmetrically from nu to mu. This is a way to describe the transport. And over this constraint set, so here this is a convex subset of the space of probability measures on the product space mu times x times x. We define the following optimization problem. So over all transport plans, we want to minimize the integral of the cost against the transport plan. If I forget about this term, this is just the standard optimal transport problem. It tells us what is the most efficient way to move the mass from nu to nu. Okay, this is a very natural notion of discrepancy or distance between the space of probability measures. But as we will see, it's a bit difficult to deal with in practice because it does not scale computationally nor statistically. So one common approach is to add some entropic regularization term in this problem. So here I add lambda times, okay, I add 2 lambda times the relative entropy between the transport plan and the product measure mu times mu. So this regularization will tend to favor transport plans which are more diffuse, and we will see that it helps on several aspects, computationally and statistically, to have a better defined object. So here, this is the quantity that we call T lambda of mu. And you can think of this as a notion of a discrepancy between probability measures, which is based on a notion of cost on the space. So it's somehow a geometrically faithful notion of distance between 2 probability measures mu times mu.
Is that too important, or?
The 2 is important, and in fact, that's why I had a little bug, because I updated my slide this morning to change it to lambda, and I thought I changed everything. So here there's a 2, so I will make sure I will comment. I hope it's consistent with the remaining, but yes, it's important that there is whether it's 2 or not. Okay, some small comments is that this function is convex in mu as well. This will be very useful. And that if I had chosen not the product measure as a reference in this regularization term, but just the Lebesgue measure, then I have a simple transformation that the resulting cost is the same plus lambda times the entropies of mu and mu. Okay. So now that I have these technical objects which are defined, we can come to the definition of barycenters. We have a notion of distance between 2 probability measures. So now we can use the usual definition of a barycenter. So for instance, when we have points in RD, one way to define their barycenter is to minimize the sum of the square distance to all these points. This gives us the barycenter. We can do the same in the space of probability measures. So here I take k probability measures, which are the ones of which I want to compute the barycenter, some weights that are normalized, so they sum to 1. And I define this functional, which is the sum. So mu is the variable, mu i's are fixed, and I want to find the nu, which minimizes this function. So this is natural generalization of the notion of barycenter to the space of probability measures. And here you have an example of how it looks like when lambda is very small. So this is essentially the optimal transport barycenter, where you have nu1, nu2, nu3, nu4, which are in the corner of these squares. These are probability distributions, which are indicators of density of shapes on the 2-dimensional plane. And you can see that when you vary the weights, you can interpolate between the various shapes. This is one also other example of application of barycenters in the space of probability measures, is to do some interpolation of shapes. But here we will be more interested in the machine learning setting, where we're in higher dimension with probability larger. So that's Wasserstein barycenters. Let me look at the definition and what we can do. So the object I just showed you is essentially when we minimize G0, so unregularized optimal transport. This is the so-called Wasserstein barycenter, in particular if I choose the square distance as a cost. So I will say it looks perfect because that's the ideal object, which does not scale very well in large-scale applications, but that we would like to somehow copy. We would like to to have an object which behaves more or less like the Wasserstein barycenter. And it looks perfect because it has very nice geometric properties, which I will not discuss. However, from a statistical point of view in high dimension, it's hopeless to try to estimate it. You have a curse of dimensionality in the rate of estimation. And also for optimization, if you want to solve this problem, it is known that this is an NP-hard problem in the dimension, the complexity scales exponentially. So we have to try to tame down a little bit our expectation and find an approximate object which behaves more or less the same, but which will still remain tractable in high dimension. So one idea, of course, is to use non-zero regularization. We have introduced this entropic regularization, so it has to be useful somewhere. So what is the effect? Maybe counterintuitively, it will tend to collapse the barycenter. Instead, so maybe when we hear entropy, we think, oh, it might dilute the density, but since this is the optimal transport plan, which is regularized, it will tend to match, like all the points from my measure mu will be matched to many points in nu, and the best way to minimize this cost when lambda is large, when I'm sending my mass to many points, will be somehow to collapse and to reduce the variance of my solution. So this induces some annoying bias, but also it's not clear that you actually improve on the statistical nor on the computational aspects. So here, all these problems are convex optimization problem in infinite dimension. So when you're in small dimension, these are convex optimization problem that you can solve on the machine. But here, I'm really talking about the large dimensional case. And here, it's not clear that this becomes more tractable in high dimension when lambda is non-zero. So we can try to have other regularization. Instead of minimizing G lambda, we can instead not regularize G, but regularize with an entropy our barycenter to make it more diffuse. So this will, of course, tend to blur the aspect of the barycenter. And again, I know of no work that show that it improves statistically or optimal on optimization aspects. And in fact, I think that this is not the case. There are still curves, but this is not shown anywhere. So these are two attempts which maybe are not satisfying. There is a third proposition, which I will not talk about in detail, which is to induce this debiasing term. This is the so-called secant divergence barycenter. So you, instead of minimizing G lambda, you subtract another term of self-transport in the objective, which tends to debias this object, but it does not really makes it more tractable in high dimension. So what can we do? We have a suggestion. I don't know if it's natural. So here we have one regularization, we have another, and they have a somehow opposite effect. One collapses the barycenter, the other one blurs it. So why not having two at the same time with this precise factor lambda over 2? So here lambda over 2 means my slides are not consistent, that in the definition of T lambda, here you should forget about the 2. This is lambda. Sorry. So if I put lambda in the definition, here I should put lambda over 2. So what I want to tell you today is that this object, it will be debiased. So good approximation and of the true Wasserstein barycenter, much better than these two ones, for instance. And also that is tractable in high dimension on the statistical and on the optimization side. So somehow by having both regularization, instead of cheating and having an object which is even further away from what we cared about, which is the unregularized object, they will compensate each other and still offer all the benefits of having regularization. All right, so that's the object we want to study. It is defined here. So here I recall the definition. This is the same as in the previous slide. We have G lambda, which is this barycenter functional, plus lambda over 2 times the entropy. This is the regularization. And that's what we want to minimize over mu. Mu is our variable. So I will call f this objective function. There are some easy properties that we can already derive, that it has a unique minimizer. It has a smooth density. So these are nice properties which are not obvious and typically do not hold when I have only one regularization. So mu star has a smooth density, whatever the new case. So even if the new case, of which I want to compute the barycenter, or direct or discrete measures, I will have a smooth positive density. Yes?
So with the way you just formulated this problem, the lambdas match here, right? One has to have the 2, and here one has to have 1 half.
No, yeah, so that's a good question. There was a typo in my first slide.
Okay, so it used to be half.
Yeah, it is to be half. You have an entropy in the entropic optimal transport problem, which is lambda, so not lambda, just lambda, and then you take half.
Yeah. Okay, perfect. Now here's the question: in the first one, when you put the lambda and the entropy, what you're making is that this t now becomes Lipschitz in the one norm or something like this, no? The t distance as a function of mu is 1 Lipschitz. So it's some Lipschitz.
Yeah, it has some regularity in various metrics, so depending on the metric.
And then with the entropy term here, you're also making this problem strongly convex in the one norm.
Yeah.
Okay, so this is now a problem that is Lipschitz gradient in one norm and strongly convex in one norm. So you have a unique solution.
Yeah, yeah. Exactly. So here, yeah, indeed. The problem G lambda of mu is not strongly convex. It's just convex. And with that, we have lambda over smooth. This one is smooth. So there are various ways to define how it's smooth. For the one norm, it is smooth. In fact, we have recent results where we show it's also smooth for the Wasserstein distance. So you have, if you move mu, again, in optimal transport sense, like for the Wasserstein 2 metric, you have a Lipschitz continuity of this object as well. In fact, smoothness, like you have second order regularity. So this T lambda is very regular. G lambda of mu is very regular. And we had a non-regular term because here this is not continuous, at least for the Wasserstein metric, but it makes the problem strongly convex. And yes, that's why we have uniqueness. Maybe one comment for specialists is that when you regularize with respect to the Lebesgue measure in the transport plan, what you get is lambda h of mu. I mean, it's equivalent to having the same problem, but instead of lambda over 2, this would be lambda. So you over-regularize when you take the Lebesgue measure as a reference in the definition of entropic optimal transport.
And your proposal is to solve this formulation once.
Yeah.
I will have a comment later.
Once? What do you mean by once?
So you just solve this formulation.
That's the variational problem that defines my object of interest, which I will go over. Then in practice, maybe we can discuss. But yes, we solve it once, it defines my object. Yeah. And by the way, how do we solve it? So there are various algorithms we can think of. One which I want to talk about today, this is this following a noisy particle gradient descent, which is very simple to define. You just take m particles in your space. You define mu x, the point cloud, so the empirical distribution corresponding to these m particles that you initialize randomly according to some distribution. And you will just run gradient descent on G lambda of mu x. So here, that's where it's very important to have a smooth G lambda. But you also will add noise, which will account for this entropy. And that's something I will talk about in the third part of this talk.
Sorry, it's the minimizer of it, regardless of lambda? Or,
sorry?
Is the minimizer unique regardless of lambda?
Yeah, when lambda is strictly larger than 0, the minimizer is unique. Otherwise, if lambda equals 0, it's not always the case.
But it's not the same for different lambda.
It changes, yeah. Mm. Yeah, the minimizer depends on lambda. Yeah. So I will talk about 3 aspects depending on time. But I have a very good timer here. 6 minutes left, so I will talk maybe about a few aspects. Approximation, estimation, and optimization. So the 2 first parts are only 1 slide long, so maybe, hopefully I can go through them. So first I want to convince you about why this lambda over 2 is the good factor in front of the second regularization, the outer regularization. And to understand that, we can look at this theorem, which gives a small lambda asymptotic expansion of the cost T lambda. So I take the square distance cost, which is the most natural one, I would say, when we do optimal transport. And I assume that mu and nu have smooth densities. Then this entropic optimal transport cost admits the following Taylor expansion, which is the unregularized optimal transport minus lambda over 2 times the entropy, okay, plus lambda squared times the second order term, which is related to the regularity of my marginals, their Fisher information. It does not matter for this talk what is the specific expression here, but you should know that if mu and nu are smooth, this is finite, and so I have this as a second order term. So here you see that it's very natural that if I add lambda over 2 times the differential entropy H, I do not care about that of mu because I'm only optimizing over mu in my Barycenter formulation. I really cancel the first order approximation error, and immediately the approximation error will drop to lambda squared. So that's this expansion that can justify the important role of this lambda over 2. So in particular, if I make the smoothness assumptions, which allow essentially to have this finite of mu, we will have that my regularized barycenter with this double regularization will have a suboptimality gap in the Wasserstein barycenter objective of order lambda squared instead of lambda for all the other kinds of regularization. So I win one order of approximation, and you can, in some setting, translate the suboptimality into actual approximation bounds from the true barycenters. So here I will not enter into these details. There are many settings where from this kind of suboptimality, we can derive good, like precise approximation bounds of the true barycenter. So that's for the approximation part. And
what are the hidden constants there?
So the hidden constant, it depends on lambda. I can tell you it's d lambda divided by 2 times logarithm of 2 pi lambda. So it depends on lambda, but not on the marginal. It's really a constant that does not change here.
What about in the corollary? So it's also an order of numbers.
Yeah, here this constant hidden depends on this Fisher information terms. Yeah, we could define what it is. It depends on the regularity of the barycenter and of the marginals. Now let us discuss a little bit about estimation. Let's assume we have random independent samples from our marginals nu, 1, etc. until nu k. And you can think of them as smooth densities of which we only have statistical samples. I mean, we only have access to samples from these densities. And we would like to estimate our barycenters still from this incomplete information. So for that, we can just simply define mu hat lambda, the barycenter of the empirical distribution. Okay? So I take my point clouds, I compute their barycenter. It will still be a smooth density because, as I mentioned previously, the barycenter is always a smooth density. And here we have the following estimation upper bound. So the relative entropy or the Kublai-Kleibauer divergence between my estimated measure using this empirical distribution and the true one. It has some dependency in lambda, which degrades as lambda goes small. That's expected. But also in terms of the number of samples that I've seen, it decreases at 1 over square root n rate. And this is independent of the dimension. The rate is always 1 over square root n, which is interesting when we want to scale to higher dimension of this object. Okay, so here I will skip the proof so that I can at least give a few words to the optimization part. Let me talk about the optimization aspect. So first, what is done usually to compute Wasserstein barycenter? So if I have a small scale problem, for instance, if I have only a few samples and a few marginals, so k and n are small, then I can use a so-called multi-marginal formulation, but it will scale as n to the k. So it's exponential in the number of samples. So we usually do not scale at all in machine learning applications. When you're in small dimension, you can always grid the space and look for the barycenter on your gridded space. But this again will scale exponentially bad in the dimension. But for large scale problem, when all these quantities are large, there is so far no solution. In fact, we know it's NP hard to actually compute barycenters. And so far what we know is some heuristics or fixed point techniques with no convergence guarantees in general. So here I will talk briefly about what we can say about the algorithm I mentioned. But since I'm a bit running out of time, what I will do is show you how it behaves in practice. So let me show you this example where I have 3 marginals in blue, green, and orange, nu1, nu2, nu3. And in black, this will be my point cloud that evolves through this optimization algorithm. So here I just run gradient descent on G lambda, and we see this collapsing effect because I'm actually optimizing G lambda. Here, in addition of having no theoretical guarantee, I also have this stronger bias. I converge to an object which is very different from here. What we would like to obtain is something like that, which is how the true Wasserstein barycenter will look like, these two dark clouds. While when I run this noisy gradient descent, thanks to this noise, I converge to a much better barycenter. And I'm also able to escape stationary points. So since I run out of time, I will skip this example. I'll just show you briefly the theoretical guarantee that we can have. So this is, in fact, a result that applies more generally to larger class of problems, which have been proved also independently by Mitanda, Wu, and Suzuki. A certain general guarantee for mean field Langevin algorithms, which tells us that at least when I have an infinite number of particles, these dynamics will converge exponentially to the global minimizer. So since I run out of time, I will stop here and take a few questions.
If I did not misunderstand, I think you can convert your guarantee from lambda to lambda squared within the Wasserstein distance. I think what you're doing
for the approximation part.
Yeah, I think if you allow yourself to iterate, because what you're doing is actually proximal point method. So if you go to your problem,
yeah.
So this problem is the proximal point applied to your smoothed objective with a center point of equal distribution. So you start with an equal samples and you refine it with your methodology, right? So you iterate
you
until.
You can see, okay, what you're saying.
So
I start from like the Lebesgue measure as the reference.
Yeah, uniform, let's say,
yeah,
right?
Uniform, and then I replace my reference measure by the first solution.
By the measure that you fix. Yeah. By iterating this, you should be able to go from lambda towards lambda squared, I think, for your guarantee on the Wasserstein.
Yeah, so the issue is that when you do this, you obtain another problem with a smaller regularization parameter to solve each time.
Okay.
And the guarantees degrade very rapidly when lambda goes to 0.
Okay. I mean,
so it's important to have good guarantees for non-asymptotically small lambda. And this proximal step, I mean, this interpretation, it still leads to issues that you have.
But you're not going to change your lambda. The lambda is fixed.
I see, but
anyway,
so
I think
we went through this line of reasoning.
I think we can discuss. Yeah, we can discuss.
But I think it doesn't solve the issues of small lambda. But we can discuss.
Yeah. So maybe I didn't get the basics. Would you go back to the experiment slide? So
yeah.
If lambda is 0, do you obtain a single point?
No. So when lambda equals 0, I should obtain something like that. Of course, here I cheated a bit because I solved it with non-zero lambda, but I used a very small lambda. And this is the true Wasserstein barycenter, I would say, in this setting. It looks like that. It's not a point. It's the proper notion of average, I would say, for this definition of these 3 probability measures. Notice that here the blue measure is bimodal, so that's why the barycenter is bimodal.
I see. So can you somehow extend this kind of idea to like a higher order moment? Not the barycenter is more like a mean, right?
Barycenter is like a mean. Okay.
Can you like extend it to like estimating the variance? Or?
That's a good point. So you can do statistics in Wasserstein space. So here I will talk about the unregularized case because I did not study at all the regularized part. But there is all this notion of doing statistics in Wasserstein space. Usually you choose one template measure as a reference. You compute all the optimal transport plans between your template and your data set. And this gives you like kind of L2 coordinates, and then you can do all the statistics you want, so averages, variances. So that's possible, yes. But
computationally, it might be,
that's not something I thought about.
Yeah, thank you very much.
I'm not sure. Okay, I'm not sure if you said it, but when you do noisy gradient descent, does the noise depend on lambda?
Yes. So when I do noisy gradient descent, the noise has to be exactly. So I skipped this part, but here this is the equation. This is Langevin. I mean, a mean, a nonlinear generalization of Langevin, and the noise is square root lambda. That's what. It needs to match the regularization I have in the entropic optimal transport problem.
Okay. Thank you very much. So I'm interested in the ratable convergence with the sample size. So you have a 1 over squared n convergence rates. It is about the convergence to the true with the regularized objective. Okay, use the lambda. So if you consider about the bias induced by lambda, so then I guess there appears something like a lambda square additionally.
No, yeah. So that's a good question. The question is, can we actually close the story and actually estimate Wasserstein barycenters using these tools? The issue, no, it's here, is that here the dependency in lambda is exponential in the dimension. So when you want to make lambda small, you'll quickly run into issues. And if you try to find the sweet spot, what is the best lambda as a function of n, in fact, to recover the curse of dimensionality, you typically get rates which are the order n to the minus 2 over d, which is exactly what we have via naive estimator of the Wasserstein barycenter. So it does not fully solve the problem. It's just we have a different object, which looks a bit like the Wasserstein barycenter, but we should not really think of it as a way to estimate Wasserstein barycenter because it does not improve over the naive estimator. It's as good as it.
So, okay, so the naive estimator becomes something like the optimal rate in the non-parametric statistics, like n2 minus some.
We can do better, yes. So we can do better, but with. I'm not sure about the Barycenter, but at least for estimating transport maps or transport costs, we can do better, but with estimators which are not computationally efficient. So that's a good point here. For computationally efficient estimators, we do not know how to make better than n to the minus 2 over d.
Okay.
In general, for all Wasserstein related objects.
Okay, thank you very much.
I'm Nitanda, so thank you for bringing up our result. So
seems to me that I did not say the names correctly. I don't know.
Yeah, correct. Yeah, thank you so much. And so I simply want to know the details. So how do you calculate the gradient of the objective? So which involves the computation of entropic optimal transport. So
yeah. So here, at each step of the algorithm, I have to compute the gradient. And the gradient of this objective requires to solve entropy regularized optimal transport at each step. So you take, in practice, what I did is just a few synchrone iterations. So this algorithm, since I can use the warm start because I'm only moving my particles a little bit at each step. In practice, this is like a few matrix vector multiplication that can compute it. But yes, there is a subgroup.
Yeah, thank you very much.
All right, let's thank the speaker.